All right. Hello, everyone. I hope you got inspired by my short talk and are here for the details. Nevertheless, this will be a standalone talk, so you don't feel bad if you missed the short one. So the topic of this talk is reionization, and in particular, trying to understand the sources of reionization using Lyman-alpha emission in galaxies. This is work done in collaboration with an international team. I want to particularly highlight the contribution from Rohan Naidu that was quite fundamental to this work. So the sources of reionization, besides being interesting on their own, had an important impact on how reionization happened. In particular, the timing. On the left, you can see the evolution of the average neutral fraction in the universe as a function of redshift. For two extreme models, blue and red, whether where either bright galaxies dominate the reionization budget or late or faint ones. And bright galaxies give you a late and rapid reionization because it takes some time to form these bright galaxies in the early universe. The data points seem to suggest they seem to point towards this scenario of bright galaxies dominating the reionization budget, but the error bars are quite substantial. The topology is affected by reionization as well, as illustrated by on the right. This is, for example, you can see a topology of reionization, some ionized bubbles, in a model where faint galaxies drive reionization. And now I'm going to switch to a model where bright galaxies drive reionization. You can see there are actually less bubbles. Bubbles are rounder, they are bigger. It's quite different. So both timing and topology are sensitive to the sources. If you want to understand the sources of reionization, what you really want to know or to measure is the mass dependence on the ionizing output from galaxies. Ionizing output is the production of ionized photons while they can escape from galaxies. So you can have a high production, but if those ionizing photons cannot escape from their birth clouds, it's not really relevant for reionization. And vice versa, globular clusters have no gas around them, but they don't produce a lot of ionizing photons. So you need to look at this in a couple of ways. So the escape fraction among these two is the most difficult property to measure. That's because the ionizing flux is faint, but particularly because intergalactic gas between galaxies and us absorbs ionizing photons. At redshift 6, basically no ionizing photon can be observed, and even at redshift 2 to 3, we only observe on average half the ionizing photons, and in particular the source-to-source scatter is really substantial. You can solve this by stacking large number of galaxies in independent sidelines, so those random stochastic transmission variations average out, or you can look at very low redshift analogs of high redshift galaxies where there's basically not a lot of gas between you and the galaxy. These both have their uncertainties and limitations, but these kind of approaches, they point towards the suggestion that the Lyman-alpha line in emission from galaxies is really the PANACEA, which is a Greek demigod for something that solves all your problems, like a cure that solves everything. Maybe that's a bit too optimistic, but it's very promising, I would argue. The Lyman-alpha line profile is illustrated on the right. The shape of that profile correlates very well with the directly measured escape fraction of ionizing photons, shown on in this right diagram. The shape is something that's much easier to measure than the escape fraction. And also the equivalent width, which is even easier to measure, just the line flux divided by continuum flux, correlates with the escape fraction for stacks of galaxies. Of course, these correlations, you need to be aware of the selection functions that were used in order to drive these correlations, and extrapolating correlations to untested regimes is always challenging, it's dangerous. But I think this is very promising, using Lyman-alpha to learn about Lyman continuum scale. So in our work, we try to do this at high redshifts, redshift 2 directly. These results came out a few months ago on the archive and in these two papers. So again, highlighting Rohan Naidu, we we try to co-first author both papers. Please discuss them as such. Still, because it's not really possible to do that. We have these two papers, and both these papers actually focus on slightly different topics. I'm addressing both in this talk. So these observations that these results are based on come from the X-SHOOTER Lyman-alpha survey at Redshift 2. This is a survey of 35 Lyman-alpha emitters with X-SHOOTER, which is the wide band spectrograph for these galaxies. And this redshift, it covers Lyman-alpha to H-alpha. So it covers all the important emission lines and the rest from UV. That really allows us, that really allowed all the results we are finding. This is a stacked spectrum of such a typical Lyman-alpha emitter. You see very strong emission lines that point towards young ages. Blue UV slope, again, young ages, low dust content. The sizes are compact. Star formation rates are relatively typical for their mass, slightly above the main sequence, but not extreme. And we do detect high ionization UV lines, like carbon-4, oxygen-3, helium-2, with equivalent weights around 1 to 2 angstroms. And those really point towards very massive and metal-poor hot stars that are present in these galaxies. So for this particular project, what's really relevant are the high-resolution Lyman-alpha profiles. The resolution is about R5000. We have systemic redshifts, which allows really to interpret these Lyman-alpha profiles for almost all galaxies. And for 2 galaxies, they are too faint to see any red-frame optical line, like O3 and H-alpha have been used for the redshifts. The sample is purely Lyman-alpha flux and equivalent width limited selected. So very similar, it's the same selection technique as Lyman-alpha luminosity functions use. So we can directly translate these results to luminosity functions and global averages, which I'll do at the end of this talk. So the line profile of Lyman-alpha correlates with the escape fraction in 2 ways. One is the most well-known, which is that the peak separation of these 2 lines, the two lines originate from a radius transfer effect. The peak separation traces the column density, which is directly associated the fraction of ionizing photons that can escape. Illustrated here, the narrow peak separations mean little scattering, little hydrogen gas, therefore high escape of ionizing photons. It's an empirically calibrated relation based on isotope et al. That's understood theoretically. In addition to that, the most extreme known leakers all show clear Lyman-alpha emission at the systemic, typically in a triple peak. We see a few of those examples in our Redshift 2 sample as well. This peak likely originates from Lyman-alpha photons that can escape directly from the gas without scattering. Lyman-continuum photons can escape as well in through such paths. It's very unclear how to use this double peak separation for these kind of systems because there are more than 2 peaks. So therefore, we introduced a new metric called Lyman-alpha Fsen, which is the central Lyman-alpha flux. It's really just the flux at the center divided by the total Lyman-alpha flux. Very simple. By combining the peak separation and the central Lyman-alpha flux, and calibrating that to low redshift analogs with very clear measurements of ionizing photon escape, we calibrated the Lyman-alpha profile to infer the ionizing photon escape fraction and applied that calibration to our survey. So we find that roughly half of the galaxies have a low escape fraction of ionizing photons, lower than 5%. Half of them actually, the other half, actually have very high inferred Lyman-continuum escape fractions, at least 20%. There are no significant differences between mass, star formation rate, and UV luminosity. It's quite interesting to see this roughly bimodal distribution. We need more, I would argue, we need more statistics to really test whether this distribution is bimodal or not. What's clear is that a significant fraction of Lyman-alpha emitters seems to have a very high escape fraction of ionizing photons. We stacked both samples, both subsets, and to see what differences are associated to a high or low escape fraction of ionizing photons. I want to stress, you really need to separate galaxies based on Lyman-alpha line profile in order to do this at high redshift. Because if you separate galaxies by detection of Lyman-continuum flux at high redshift, I think you tend to select fortunate sidelines in the intergalactic medium, which has nothing to do with the galaxy. The Lyman-alpha profile actually traces the escape fraction in the ISM of the galaxy, and the CGM probably as well. So what we find in these two stacks, we find in the high escape stack, we find that the Lyman-alpha escape fraction is much higher than the low escape stack. This is expected, and it goes towards the direction that indeed high escape of ionizing photons is also higher in that stack. In the low redshift leakers, if galaxies have a high escape fraction, their ionizing photon escape fractions and Lyman-alpha photon escape fractions are similar. Therefore, we assume a fiducial value of 50% for this high escape stack, but 20 to 50% is allowed. Another motivation for this fiducial value is that this would place our results in consistency with stacking results of Lyman break galaxies split by Lyman-alpha equivalent width. And Lyman-alpha emitters in that stack then seem to have an escape fraction of 25%, given that half of them actually have an escape fraction, some number, and the other half almost zero, as in our survey. You must get 50% for the leaking Lyman-alpha emitters. So what are the conditions associated to that leakage? So it's really, we see quite a lot of differences. So magnesium-2, which is a resonant emission line, and it's going to be observed by JWST a lot because it's promised to trace Lyman-alpha and Lyman continuum escape. We do fully verify that. The magnesium-2 profile is different if you split your sample in a Lyman-alpha profile. High escape is associated to a magnesium-2 doublet. That's why the blue line is much stronger than the red line, which you expect for low column density gas. And a low escape, magnesium-2 is redshifted with respect to the systemic, and the lines are equally strong, which is, I think, it's very promising. So we do see that the ISM conditions are also very different. High escape of ionizing photons is associated to very high ionization parameter, basically no dust, while low escape fraction has a more normal ionization parameter and somewhat more dust. And note that our low escape stack is basically low escape among Lyman-alpha emitters. It's a lot of galaxies are not even Lyman-alpha emitters, so not even Lyman-alpha photons can escape, which suggests that our low escape stack is basically low escape, high escape, relatively high escape among all the low escape galaxies that are around. But nevertheless, we still see remarkable differences to galaxies with a high escape fraction. So what I think is most interesting is that we actually see that the galaxies that have escape of ionizing photons also have younger stars with stronger nebular carbon-4 and helium-2 line emission, absent in the stack of non-leakers, but present in the stack of leakers. The optical emission lines are also much stronger in the stack of leakers, even though like the non-zero escape fraction actually reduces those line strengths, but they're still stronger than in the sample of non-leakers. And this really suggests that these galaxies that we select to have a low escape fraction, a high escape fraction of ionizing photons, they also tend to be the ones where a lot of ionizing photons are being produced. Hard ionizing photons, but also normal H1 ionizing photons. So that confirms that, that galaxies actually are able that ionizing photons can escape from galaxies when those photons are still being produced. The interpretation for that is basically very simple, naive picture that if you form a star cluster or a bunch of star clusters together, initially in the first few mega years, those stars are still surrounded by their birth cloud. And the ionizing photons are absorbed and the Lyman-alpha photons are also trapped and scattered just within that gas. After a few mega years, the feedback from those massive stars will have dissipated the cloud. And what you get is Lyman-alpha photons, they can fully stream out of those clouds towards the observer, and the ionizing photons can escape as well. After a while, the first dust starts being produced. You get some more hydrogen again, because feedback weakens, some neutral hydrogen, and that process will continue until some stabilization. Of course, the time scale is not the only relevant process here. It's also a particular viewing angle. It could be that the viewing angle plays an important role in whether we observe a galaxy to be in a specific phase or not, in addition to the timing. What is, I think, very useful is that our survey allows to know these statistics. We know that half the Lyman-alpha emitters are observed in this phase along this sightline. And we also know that Lyman-alpha emitters constitute about 15% of the star-forming galaxy population in redshift 2, but they are quite rare. And most galaxies in redshift 2 are actually on this phase 4. But it may be different across cosmic time, as I'll argue. So these statistics allow us to get a global picture of what's going on. And in order to, so background of that is this ionizing emissivity over cosmic time that's known from the UV background measured by quasar absorption line studies. And the emissivity is a product of both, it's a combination of both quasar emissivity and star-forming galaxy emissivity. Quasars are much more common at later times. So at early times, the emissivity is likely dominated by star-forming galaxies. And what's interesting is that this emissivity is relatively flat from redshift 3 to 8. It doesn't evolve, it evolves within an order of magnitude. While over the same period in time, the cosmic star formation rate density, just the produced number of ionizing photons, opposite to the number of emerging ones from galaxies, evolved substantially over that time period by at least an order of magnitude. And that implies that the average escape fraction of ionizing photons from the galaxy population needs to evolve very rapidly. It was much higher at very high redshifts than it is today, and also at redshifts 2 to 3. How to explain that is a bit tricky. And what we just noticed is that if you make this plot of the emissivity and the star formation rate density, in this case, unobscured star formation rate density from the UV, which is likely more associated to the escaping ionizing photons than the obscured star formation rate density. The emissivity that you need from the galaxy population is quite similar to the evolution of the Lyman-alpha luminosity function, which we use to argue that well, let's just do a calculation of the galaxy emissivity, assuming only Lyman-alpha emitters contribute to the emissivity. If you actually do that, as detailed in this paper, with relatively bright galaxies, with the escape fractions that we measured, and assume all these things are constant with redshifts for the subsample of Lyman-alpha emitters, that's crucial, and with luminosity, we find that you can explain this relatively flat emissivity very well. You can also explain reionization, the timing and the timeline of reionization, but you need to do some assumptions on what Lyman-alpha is doing in the Epoch of Reionization. We can discuss more about that. I think it's interesting to consider at the end, what does a Lyman-alpha driven emissivity mean for the general galaxy population? And in our model, only Lyman-alpha emitters with a limiting luminosity above the selection limit of our survey has an escape fraction of 25% on average. All other galaxies have an escape fraction of 0. If we then link Lyman-alpha emitters to Lyman break galaxies on a statistical basis, using the luminosity functions, we can estimate how the escape fraction of ionizing photons depends on luminosity and on redshift. The redshift dependence is kind of matched with what you need. You get a very strong redshift evolution, increasing towards higher redshifts at fixed UV luminosity. And we also find that the escape fraction peaks at a very distinct luminosity as well, which is, I think, a very interesting and nice result. This peak originates from the difference in the luminosity functions, particularly the bright and the brighter part of this diagram. The shape, the position of this peak is basically determined by the limiting Lyman-alpha luminosity that emerges from leakers. I'll discuss that in a few seconds. So what this means, this model means that the ionizing photons that get out of galaxies are roughly distributed in terms of luminosity from the galaxy where they came from in a log normal way like this. It doesn't depend strongly on redshift, and it implies that most of the ionizing photons escaped from galaxies with a stellar mass of about 10 to the 8. It's crucial that this peak position around -19 here actually assumes that the escape fraction is 0 for fainter Lyman-alpha emitters as well as non-Lyman-alpha emitters, which we never showed. If fainter Lyman-alpha emitters would actually have a non-zero escape fraction, our distribution of the ionizing budget would shift towards fainter luminosities, as illustrated here, and therefore also towards fainter masses. And we don't know whether this is happening or not, but fortunately we were awarded a program to look at lensed Lyman-alpha emitters that are intrinsically faint and try to indirectly measure their ionizing photon escape fraction to see whether this is the case or not. Let's see, I've already gone over my 20 minutes, so I'm just going to leave you here my summary. I am happy to discuss this either now or during the conference or by email, or if you are searching for someone to give a talk at your meeting or a seminar, I'm always available to do that. Thank you.